Let's take a look at Coulomb's law. So we talked about the way that like charges repel and opposite charges attract. Now we'd like to know how big is that attraction or how big is that repulsion. And that's what Coulomb's law is all about. How big is that force? And we can make some pretty good predictions as to the nature of that force if we just think about it a little bit. So we've got two charges. Let's make them, say, a positive charge and a negative charge so that we're going to get an attractive force between them. Now, we're certainly expecting that we're going to get a bigger force here if those charges are bigger. If you got more charge, you're expecting more force. So we're certainly expecting a bigger force if you have bigger charges. The other thing that we're expecting is that, well, if I move these charges back, if I increase R here and move those charges back from each other, there should be less interaction, and that means less force. So we're going to get a bigger force as well if the separation decreases. And the equation for the force between these two charges is given by what we call Coulomb's law. So the force will equal the product of the charges, Q1 times Q2, and that of course means that if we increase either Q1 or Q2, we're going to get a bigger force, divided by the separation distance squared. And we're going to talk about why it's squared in a second. So that means if R gets bigger here, you're dividing by something bigger and you're going to get a smaller force. So increased separation, smaller force. Of course, we need a constant out front, and we use this Coulomb's constant K. It's equal to 9 times 10 to the 9th. And this here, that equation, tells us the force between 2 point charges, and that's called Coulomb's law. So Coulomb's law is an example of what we call an inverse square law. That just means that the force is going to vary as 1 over the separation distance squared. This turns out to be very common in nature. We get it in universal gravitation, where the force is equal to a constant times the product of the two masses. Any two masses in the universe will attract each other, divided by that separation distance squared. And as we just denoted with Coulomb's law, it's equal to a constant times the product of the charges divided by the separation distance all squared. So here you can see that we have exactly the same form for gravity as we do for electricity. And why do we get these inverse square law forces? Well, it's easy to understand if you think about a can of spray paint. If we spray some paint and there's a close wall, let's say at 1 meter away, and we spray for, say, 1 second, then we'll get a certain thickness of paint here. However, if we move our wall back another meter and we spray out, then the paint is going to spread out over a larger area. So if we spray for the same amount of time, we're going to get a lesser coverage of paint. It's going to be 1/4 as thick of paint here as there will be here. And then if we move out another meter, 3 meters now, then our coat of paint is only going to be 1/9 as thick. And then if we go out to 4 meters, it's going to be 1/16 as thick. So we're simply spreading out our paint over larger and larger areas. And that's the same way that it works with the gravitational field and the electric field. You can think of the electric field as simply being spread out over a larger area sphere when you're at larger separation distances. Now, theoretically at least, Coulomb's law only applies to point charges. So we'd have to be talking about, say, a proton and an electron, which we would consider point charges, and then we could use Coulomb's law to figure out the force between the point charges. However, if we have macroscopic type objects that are charged up, and if they're quite close together, then we can't use Coulomb's law. But remember, anytime we separate the charges enough, if we get them well spaced here so that R is quite large, then it's going to be okay to use Coulomb's law. So as long as R is much, much bigger than the size of the charged objects, then you can use Coulomb's law. when I wrote down Coulomb's law, I wrote it as the force is equal to some constant k called Coulomb's constant times the product of the charges divided by the separation distance squared. However, if you look into your data booklet, you'll find it's written this way here. And just by comparison, you can see that that 1 over 4 pi epsilon 0 must be equal to k. Now, k has a value, as I said, of 9 times 10 to the 9th Newton meters squared per Coulomb squared. The epsilon 0, called the permittivity of free space, has a value of 8.85 times 10 to the minus 12. But what the permittivity of free space does is it allows us to consider situations where our charges are not in a vacuum. Let's say our charges are in water. We could still calculate the electric field. And the way that we do that is, instead of writing epsilon naught here for the permittivity of free space, we're going to write 1 over 4 pi, just epsilon. And that epsilon is going to be the actual permittivity of the substance. And the way that we get the actual permittivity is to multiply one of these numbers here, called the dielectric constant. It's also called the relative permittivity. So for water, for instance, it has a dielectric constant, a relative permittivity of 87.9. And I'm going to use a letter K for this relative permittivity, or the dielectric constant. My actual permittivity will equal K times the permittivity of free space. So in the case of water, I would get an actual permittivity of 87.9 times 8.85 times 10 to the minus 12. What that number really means is that the electric fields, the electric forces, are going to decrease by a factor of 87.9 as compared to a vacuum. So in any substance other than a vacuum, that electric field is going to decrease. That's fairly easy to understand too. Let's consider the effect of putting some substance in between parallel plates. So that substance might be water. We connect a battery across our plates. So we'll get a positive plate and a negative plate. And that would produce an electric field. Now, if we consider any of the water molecules, or any of the molecules in whatever substance we're talking about. So if this is a molecule, there's always electrons in molecules. And those electrons are relatively free to move around. And they'll get attracted to the positive side over here, leaving behind kind of a positive hole back here. We're going to have more positive charge on this side, more negative charge on this side because of a slight movement of the electrons. Well, positive here, negative here, that means the electric field of the molecule is opposing the electric field of the plates. And that's what happens. And that's what happens whenever you put charges in substances. The molecules create their own electric field, which opposes the electric field that's already present. So they reduce the electric field, and they would reduce the force between charges. Okay, let's try an IB example that uses Coulomb's law. So what I'd like you to do is to read over the question carefully, try it out for yourself, and then come back for the answer. So what we're doing is we're comparing this force here between Q2 and Q1, which I'm going to call Fxy, to this force here. I'm going to assume the forces are attractive. It really doesn't matter. To this force here, which I'll call Fxz. Now, all the charges are equal in magnitude, and that means that product of the charges isn't going to change for Fxz compared to Fxy. So if I just write down Fxy, it's going to equal K times the product of the charges Q1, Q2, or I'll just write that as Q squared, divided by the distance squared, and the distance was simply 1. And if I compare that to Fxz, well, the numerator stays the same. The only thing that's going to change is the denominator, because now we have a longer distance. And what is that distance? It's going to be 1 squared plus 1 squared, or the square root of 2. So we've got to put the square root of 2 meters all squared here. And that means that I can rewrite this as 1 over 2 times kq squared. Well, kq squared, that's simply Fxy. And that means Fxz is equal to 1/2 of Fxy. And so the correct answer here would be A F over 2. So in summary, whereas two masses can only attract each other, two charges can both attract and repel. They're going to attract if the charges are unlike, one positive, one negative. They're going to repel if the two charges are like. But the form of the equation for the force in both cases is the same. We've got the force for gravity equal to the universal gravitational constant times the product of the masses divided by the distance between their centers, all squared. And Coulomb's law, or the formula for the force between charges, is given by Coulomb's constant times the product of the charges divided by the distance between those point charges. And we also expressed this equation here in terms of the permittivity of free space, where it was equal to 1 over 4 pi epsilon naught times the product of the charges all over the distance squared. So this is the equation in a vacuum. If you're in some other substance, then the force would be equal to 1 all over 4 pi k times epsilon 0 times the product of the charges all over the distance squared. This k here would be called the dielectric constant, also called the relative permittivity, and that k is always going to be greater than or equal to 1. And that's all for today, folks. Thank you very much.